Okay, so now that we've seen what we kind of want from a type checker, let's actually go through the full details of how will we extend lettuce to include type checking. All right, so type checking in lettuce. So let's remember what we are kind of wanting to do. We want to come up with new syntax for lettuce so that we can say like, let x be a num equal to 10 in let f be a num to num, which is a function, right, that takes in, as you should, or as it should, y as a num. It returns y plus 10 in, and then we have, say, let rec of g from num to num. And this is just going to be some function, right, that takes in, say, another num, and maybe calls g on y. Right, and we're gonna, so we want to be able to add these annotations in, and the nice thing is that there's only so many places in our language that we actually have to add it. And I've put them all here. So if we go through this, right, for any of the let statements, we're going to want to annotate what is the variable that we're going to be binding to, what is that going to be, right? So we need to change the let bindings to include some sort of type statement. We also are going to need it for function definitions. Right, so in this case we have num to num. We're also going to want to put it into the parameter of the function. So it's the parameter as well. Although it's not necessarily technically necessary, but it's nice to put it there anyway. And then also obviously let rec, which is sort of the combination of a function definition and a let binding. We're going to also want to have, that's function, type annotations there and in our parameter for the function. So this is what we want our concrete syntax to eventually look like. So to do that, what are we going to do? We're going to extend our language a little bit, right? So I mentioned we really only have to change those statements. So lettuce, right, everything's an expression, and we have our const of a double. We have a bool const. I think I mentioned that one before, but right, this keeps track of our bools, just wraps it into our abstract language, plus of E1 and E2 greater than or equal to of E1 and E2, right? And right, the goal here is we want to be able to definitely be able to say that E1 and E2 are both numbers, right? That's our goal, is to write a type checker that can go through and make sure that everything is well typed as we go. So we have all of the standards, right? And we're going to have to change let. So we'll have string type and then our two expressions. Right, so the addition here is, it's the addition that you'd assume, right? So let x, that's the string, num is the type, 10 is the expression here, and then everything after the n is the second expression. Similarly, we're going to change fundef to be, let's see, string, what do we have? Fundef, right, we're going to have a string for our name, and that needs to be a type. Right, this is really from the let f, right, that's our let statement. This is the definition for fundef, is this little use of num there. That's where this type is. So string is y, num is the type, or type is num, and then we have the body, right, which is an expression of the function. What else do we need? We need the let rec, which combines the two essentially, right? So we have string, which is going to be the name, its type, and then a string, which is going to be the parameter and its type. And then we have the body of the function, right? And then the everything after the function, the n. So we're going to have to make sure to define these rules and figure out exactly how they work. But, and then also remember, when I say this capital T type, it's because we came up with the abstract syntax for our type structure, right? So just as we have expressions, we also now have types, which are just going to be num types, bool types, or a function type, which takes in two other types, right? It takes one type and spits out another type. And that gives us the entire hierarchy of all of our types, right? So that's what these capital T types should be, is one of these format. Let's see. So yeah, let's look at some examples of things that we want to check. And also, right, this language, this is our normal standard lattice. We're not doing any references right now, but we are dealing with recursion, right, with the letrec. So references, we would have to do a little bit more chasing, so we're going to just ignore them for now. So, right, what do we want our type checker to do? Well, the type checker, right, it's going to be some program that should take in an annotated lattice program, and it should spit out either the type of the program or some sort of type error that says that this program is ill-typed. Right? Every one of our lattice programs is an expression. Every expression should have a type. And this type checker is just going to go through and make sure that everything is working correctly. So let's look at some of the cases that it should catch, right? So we have let x equal y in x plus 10. Right, this should throw a type error because y is undefined. So that should definitely throw an error out. We should have errors if we have something like this. Let x equal 10 greater than or equal to 45 minus 10 in x. Right, here we have a bool, and here we have a num, and we're subtracting a bool and a num, and that we don't want to allow that, right? We don't know what that should end up to be. So this should be caught by our type checker as a ill-typed program. It should throw a type error. Another case will be something like this, where we say let x equal a num. Right, so we're using our annotation in 45 in, right, if x then 10 else 15. Right, and we should be seeing, oh, this needs to be a bool, but you're given a num. So this should also be ill-typed, right? Or throw a type error. So yeah, we want to make sure that all of our variables are well declared with their own types. We want to make sure that we're not combining types when they shouldn't be combined. And we want to make sure that if the type is expected to show up, that's what we want it to be, right? So if x is a num, and we don't want to, or if we're expecting a bool here, we don't want to be sticking a num in here. So what is this type checker really going to look like? It's going to be a function just like our eval, right? It's going to be basically the same structure as an eval, but it's going to be doing something slightly different, right? It's going to be running through our lattice code, but it's going to be checking types instead of checking actual evaluations. So it should be something like this. Right, we're going to define type of, which is going to take an expression. All right, that's the program or the small chunk of lattice that we want to figure out what the type is. And then we're going to have a type environment. Right, this is alpha. We're going to be storing all of the types that we figure out there. Right, every time we bind a variable and figure out its type, we want to add it to our type environment. That way, when we see x later, we know what it is. Right, and then this should return a type or an error. Right, and obviously this is very, very similar to our eval function, which is what it takes an expression, and it takes a environment. We're not doing the version with the store right now, so it just takes an expression and a local environment, right, and returns a value. So very similar ideas, very similar process. It's just one is only doing the type work while the other one is doing the actual evaluation work. And what is a type end? Right, this is going to be a map between strings and types. right? It's just like an environment maps a string to a value. Our type environment's going to map a string to a type. Okay, well, you probably are expecting this at this point, right? So we've just come up with exactly what this type of function is going to look like. We sort of know what's going on here. And we have all of our abstract syntax, so the only thing left is to start working through our big step semantics, right? Let's see what type of actually does on various parts of our syntax so that it will catch all of these errors. Okay, so let's start with the simplest thing, right? What should type of const of D under some alpha look like? Well, we're saying all we have is this const of a double, and so that's a number, right? So we're going to return num type. And there's nothing over the top of this rule, right? There's nothing to check. Just like eval on a const just returns D, this just returns a num type because that's clearly what it is, right? That's how we sort of come down to brass tacks. What is a number? It's a num type. Likewise, type of, called it bool constant here, of some bool, let's call it B, under alpha, what's that going to be? Well, a bool type, right? Pretty straightforward. Again, nothing on the top here. We'll just call that the bool rule, right? Nothing over the top. It's just exactly what it says it is. Okay, let's go a little more tricky, right? Type of ident of S under alpha. What should this do? Well, it means that we're looking up a variable name. So we want to know what is the type of this variable. So we'll see is ID in the domain of alpha, right? So we're seeing is, or sorry, not ID, but S here, right? Is this variable actually in my type checker or my type environment, right? And if it is, then we're just going to return whatever that type is. All right, so this is ident. Okay. What's the error rule for that, right? So type of ident of S alpha, well, what's the case that it fails? S is not in the domain, right? So it's not defined. Then this should be a type error. Right, this is that lettuce program that I wrote up where we said let x equal y in. Right, and we didn't define what y was, so we would throw this error. What's next? Let's start to go to our binary operations. So let's do plus. All right, so what should type of plus of E1, E2 under alpha look like? Well, we need to know what the type of E1 is, right? So type of E1 under alpha, right? We want to check that is, well, what do we need in order for it to work properly? We need that's a num, right? And likewise, we need to know that type of E2 under alpha is a num. And obviously, if they're both nums, then we can add them together. And so we get a num out. I'm going to switch over to the concrete syntax, but just remember num is num type. The right bool, it's bool type. And the function types I'm just going to do with our little double arrow, right? Num to bool, that kind of thing. Just to make it a little easier to write out all these rules. So yeah, this is going to be our plus OK. And then what are our error rules for this? Well, very similar to the eval error rules, right? So type of plus E1, E2 under alpha. This is going to be a type error. If what? If type of E1 alpha is not a number, right? So that's going to be our plus error 1 rule. And obviously if type of E1 under alpha is a number, but the type of E2 under alpha is not a number, then of course we should throw a type error if we're trying to add those two together. Right. So that'll be our second error rule for that. So very similar to the eval, but instead of actually evaluating anything, we're just looking at the types and making sure that the types make sense. Let's look at one of our Boolean structures. I'm going to get rid of these top ones. Right, so what should type of, I got the G, greater than or equal to on E1 and E2 look like under some alpha? Well, really similarly, right, we just want to double check that when can we do greater than or equal to? Well, we need to make sure that the type of E1 is under alpha is a number, and that the type of E2 under alpha is a number. So, and then, right, this would be a bool. So this is our greater than or equal to OK rule. And obviously the same kind of error rules apply if either of them are not numbers. This one's a little more interesting, right? So if we do, what's the type of equality between E1 and E2 under alpha? Right, when is this going to make sense? Well, one way we can write this out, right, is we're going to say, let's suppose type of E1 under alpha, this is some tau, and tau is not a type error. And also type of E2 alpha is equal to tau. Then the type of equality is bool. Right, so this lets us be able to compare is, you know, true equal to false, right, because they're both bools, and so that'd be tau. We could also compare is 45 equal to 45. We'll also be able to do things like if f and g are both functions, we can say is f equal to g, right, and if they're both, say, num to num, and this is num to num, then we'll get we'll at least be able to evaluate the correct type, right? We'll get out that the type of this is bool. Otherwise, we'll throw an error if the two types on either side of the equal sign are different. But this is a fun little, this lets us do things besides just numbers, right, for equality. Let's do if then else. I'm going to get rid of the plus stuff here. So we have type of if then else is going to be, well, E is going to be the if E, then E1, else E2 under alpha. And how do we want to evaluate this? Well, this is going to work out correctly, right? We want that the type of E under alpha, this should be a bool, right? Otherwise, we can't really say if that's true, right? To say it's true means that it's a bool. It's either true or false. So we want E to be a bool. And then we want the type of E1 under alpha, say that that's tau. And we also want type of E2 under alpha to also be tau, and tau should not be a type error. And if that's the case, then this whole thing should be tau. So what's this sort of situation where this happens, right? So something like, right, this might seem a little strange that we want both E2 and E1 and E2 to evaluate to tau. And it's for situations like this where we have a function on x that is, right, if, say, x is greater than 25, then 15, else we call, say, a function on y, which gives back y plus y. Right, it's trying to avoid this situation where we have two different branches of our function, and if we go on one branch, we return a num, and if we go on the other branch, we return a num to num, right? So this entire function doesn't have a well-defined type, or at least return type, right? This takes in a num, but it returns either a num or a num to num, and we don't want this, right? We want it to make sure that it's of a formal type, a fun type. So this rule basically prevents this from happening. Now you could actually write this kind of thing up in Scala and it will typically pass, and that's because Scala contains what are called union types, right? So if you have, say, like, let's say one branch returns a bool and another returns a num, there's this other type called an any that basically supersedes both of those. So this would return an any instead of a specific thing because it could return multiple stuff. But in our lettuce version here, we're not going to have union types. So we want to disallow this stuff from happening. And that's why we wrote up our if-then-else statement in this way. Okay, so that's some of the small change, or that's how we're going to do basically everything that we haven't modified yet, right, up to the let. You can figure out your own rules for multiplication and division, all of that. They follow the same basic structure. So let's see how we implement let in this type checker. So what should the type of let of, right, we have an x, we have the type, which I'm going to call T1, a E1, which is, right, what we set x to be, and E2 under alpha. Right, what should this be equal to? And remember, we have let x equal E in our annotated notes, right, of T1 equal E1 and E2. Yeah, so how do we want to do this? Well, we want to make sure that whatever E1 evaluates to, that actually is the type that we've told the type checker that x is, right? So the very first thing that we want to do is just double check, is type of E1 under alpha equal to T1, right? It has to be for this to make sense, otherwise we'll throw an error. And, right, if we have that true, then we will check the type of E2, and, right, so we were going to check the type of E2 here, but what do we want to do? We want to bind x to T1 in our type environment. So we're going to do this under alpha, and I'm going to extend it with this map style extension, right? So x points to T1. And then this is going to give us some T2, right? Because we've gone through and we've walked through the types of E2, and that gives us something. And so if that, whatever that happens to be, T2, that's what we're going to give to the type of let, right? Because this whole thing evaluates to whatever the type of E2 happens to be. Right, what's the key part that really happened? It's this extension of the type environment. Just like we typically extend the environment when we do a let statement. We're just doing the same thing but for types instead of actual execution. Okay, so we've done let. Let's do fundef. Right, what do we want for fundef? we want to basically have something, right, that looks like function of x number, right, and then say x minus 25, right? This is the type here, right, and then we have the string, which is x, and then this is the expression, right? And what do we really want to do? We want to make sure that, we want to double check that the let statement that we're having, what do we want to do with this fundef? We want to make sure that the body extended by x points to num, right, so that we know that in the body, what is the type of x, that this whole thing evaluates as something, and that's what the whole thing's going to evaluate to, right? So we have to figure out what is the fun type of this. So type of fundef of, let's say, x, and t is our type of x, and then we'll call this the e body, right? So e body is down here, this is t, and obviously that's x. All of this under some type environment alpha. That should be, well, I'm going to evaluate the type of the body under x extended by, alpha extended by x points to t. Right, so we're saying x is of type t, now tell me what the type of the body of the function is. Obviously we'll use x in the body of the function, so we need this extension of the type environment. And this is going to be some tau, and as long as that's not a type error, then we want to pass that back to, not tau itself, right? This is a function, so we want it to be of some sort of fun type. So it's going to be, what's it going to be? It's going to take in whatever a type of t is, and what's it going to spit out? Something of type tau. Right? That is what you would expect out of this, and that's exactly what we get, right? Okay, so we have one last part of our abstract syntax to write the semantics for, which is the let rec. So let me write down a little example of let rec so we know what all the component parts are. All right, we're going to have let rec f from t1 to t2. This is going to equal a function. X needs to be of type t1, and then we have our body of our function, and then we have n, the rest of our program. All right, remember let rec is this combination of both a function def and a let statement. So as per the let statement, we have all of this extra computation down here, but as our function definition, we also have this function with the parameter in the body. We want to make sure that, right, t1 is matching our parameter input here, so otherwise it doesn't quite make sense. In fact, there's a little bit of redundancy here. We don't actually need, say, this left-hand type, but our type annotation, but it's still useful to have. Like, why not keep it around? I think it keeps the writing of it very clean and obvious. Okay, so let's start writing this out, right? So what does type of let rec of f, this is going to be of t1 to t2, x. In fact, I'm going to leave this vague as tx right now, and we'll see that we want to make sure that those are the same. Because this is a more general form, right? We might not have that the same, and we want to catch that error. So we have x, tx, e body, and then e, all evaluated under the type environment of alpha. So first of all, we want to make sure that t1 is equal to tx, right? So if those two are not the same, then we have an issue, and we'd throw an error. And then if we know that those two are the same, what do we want to do? We want to check out the type of the body, right? so type of E body with alpha, but what do we want to do? Remember, this is a recursive function, so E body contains both references to X as well as F itself. So we need to extend alpha by, well, we need X to point to Tx, right? That says that we are keeping track of that fact. And we also need F to point to, right, T1 points to T2. So we're keeping track of the type of F as well as the type of X when we evaluate the body of this recursive function. And this whole thing should be T2, right? That's the sort of given promise of our type annotation for F. If it's not T2, we should throw an error. And so if this all holds, right, then our function definition is all good type-wise. But what is the actual final type of this whole expression, right? If we think about this as an entire expression and evaluate it, what the answer is whatever E evaluates to. So the entire type of this whole thing is actually going to be whatever the type of E is. So this whole expression is going to be equal to the type of E, and then we need to extend our type mapping, our type environment, to include that F is of type T1 to T2, right? X is out of scope at this point, but we definitely want to keep our definition of F around. So that about does it for all of the semantics. I hope you were able to follow this, but even if you weren't, it's the same sort of semantics we've been doing. Just instead of actually evaluating any numbers, right, or Booleans or anything like that, we're just going through and double checking that all the types work. Maybe the boldest place that this shows up is in this letrec, where if you remember the eval for letrec, we had to modify the environment to make sure that it actually handles the circular scopes correctly, right, by making those extend recs. And here it's actually really simple, right? Because we don't have to evaluate the body of this recursive function, we can actually just extend our environment directly to say that, well, F is of this type. We don't actually need to know what F does. We just know that it's that type. So we can include that in our environment when we actually go through and check the type of E body. And it's much simpler than the actual recursion that's going on. Yeah, so I hope this makes sense in terms of basic how we would make a type checker for Lattice.